Thank you, Rosa, for that very nice introduction. It's a great honor to be here. Very nice to see you all and to be in Valencia. I think I got a few words of Spanish from the previous talks, but it seems that everybody was wondering what the future might look like. And I'm not saying this is the answer, but let's think about what's happening here. I thought I would start with just giving a landscape of AI reasoning. Maybe it's very new to many of you what that means. I'll make a case for neuro-symbolic AI, which is the title of the talk, and then talk a bit about LLM reasoning and see how that goes. So for a long time, since the 1960s, people have been working in AI. And initially, our inspiration for AI came from Greek philosophy. So Greek philosophers like Aristotle and Socrates thought about three things that humans are able to do. So the first thing is deduction. So if I say, for instance, that I have a white shirt and you spill something on the shirt, then it might get dirty. So that's a case of deduction. Induction is a case where I see things and I abstract a pattern. For instance, I may see that all swans are white, and then I conclude that swans are white always, until I see a black swan. And abduction is more interesting because abduction is what Sherlock Holmes does. If you've ever read Sherlock Holmes' mysteries and thrillers, he looks at a case, he looks at something that's happened, and he comes up with an explanation. Okay, so for a long time, people were obsessed with these three things in reasoning. But then that changed. Maybe around 1990 and 1980s, people started building machine learning models. So what are these models? These models basically ingest a lot of data. They extract patterns, and when you give it a new data point, it's going to say whether it's 1 or a 0, or a plus or a minus, a cat or a dog, that sort of stuff. So it works great. So machine learning powers Amazon, powers Google search, and many other applications. But there are some very interesting problems once you apply them to human domains. So one example is when you work in the healthcare domain, you often need an explanation of why a prediction came true. For instance, it's suspected that machine learning models are almost as accurate as radiologists when looking at X-ray of your chest. But a radiologist will be able to tell you why something is a cancerous center or not, whereas a machine learning model would not be able to give you that information. So a big question is, what is the connection between the prediction and the explanation that we have inside our heads, right? So explanation is a big aspect. Sometimes when you work in medicine, you work in logistics, you have a lot of expert knowledge, and you want to use this knowledge when you train the machine learning model, and there's no obvious way to do that. So these kinds of issues have generally led people to worry that maybe the answer is not simply ingesting more data. A more interesting point is what is called as causality, right? So causality is a point of view that everything that happens in this world is a result of some cause and effect. An example is if I start smoking every day for the rest of my life, there's a good chance I might get cancer or at least asthma. So there's a connection between me smoking and getting cancer. So the understanding of the distinction between causality and just correlation is something that we understand as human beings. So for instance, we might say, don't cross the road when it's, when the traffic is going by, because we know there's a cause and effect there. And machine learning models can't actually make this distinction on their own. They need a lot of information and a lot of input from humans to figure it out, okay? So there's a bit of disconnect. So if you look at these ideas, it's all about the way humans think. And then if you think about machine learning, it's all about working with data. So there's a disconnect here. And people quite haven't worked out what's the best way to bridge this gap, okay? One interesting development, of course, is generative AI. So people think generative AI is new, but in fact, it started with Google Translate, which came around 2007, if I'm not mistaken. 2013, we had pretty good models of Google Translate. And how does it work? So it basically looks at a large chunk of text, okay? So if you've ever seen Moana, have you seen the movie, Disney movie Moana? Yes, no? Yeah, so what happens in Moana is there's a little girl who's trying to cross to an island, and she does various things in the movie. So she builds a boat, and on the boat, there's a chicken, okay, and there's a pig, and they try to cross the ocean to go to the island, okay? So what large language models do is that they look at a context and they look at the most likely possibility that might come next, okay? So what happens is that if you feed it a lot of movies, it can pick up a pattern that seems to think that it understands what the movie is about, okay? I want you to remember this kind of graph because it's quite simplistic, but surprisingly, this is what powers all of the latest large language models, okay? The only difference is that it's trained on such a large amount of data that the patterns are incredibly good, okay? So, does it work? Do large language models work? How many of you have used ChatGPT? Well, almost everybody, right? So it works quite well for writing reports, writing an essay. Maybe you ask it questions about, can I take a paracetamol when I'm drinking alcohol? Those kinds of things, right? But there are a few issues when it comes to these large language models. One issue is so-called confabulation or hallucination, okay? Because it's working on these probabilistic paths, sometimes it can jump quite far. So you can say, for instance, is it safe for me to drive at night? And it might say, it's safe for you to drive at night provided you switch off your lights, right? Because it's taking a leap. So it says something very strange. And if you're not an expert and you're reading this, you can get quite confused, okay? Again, explainability, we don't know why they said something. So if you ask a human being, why did you vote for a political party? There's a reasoning behind it. You may not agree with it, but there's still a reasoning behind it. There's no such thing here, right? It's just going by patterns. And so sometimes you can get very strange patterns from them, okay? So even though they're impressive, they're being used everywhere. If you go on Google now and you search something, along with the usual Google search, you also have an AI mode, which is basically a large language model giving you an answer as well. So it's quite popular, but I'm not sure it's the right thing to do. Now, the question is it going to get better? Is it going to get to a point where it matches you and me, okay? Now, this is where it gets really scary. So the latest models on ChatGPT is something called ChatGPT version 5, okay? ChatGPT version 3 already had more parameters inside the network than all the connections inside a rat, okay? I know a rat is quite small, but still, if you think about it, you know, we have already built a network that's bigger than the brain of a rat, okay? GPT-4 has 1 trillion parameters, okay? The number of connections in our human brain is 100 trillion, okay? So we are just 100 factor away from replicating all the connections of the human brain. But if you think about the fact that it's trained on such a large size, it seems very strange that they make such silly mistakes, right? The other thing is if you look at the amount of text, okay? So GPT-1 already was trained on more data than English Wikipedia, okay? And English Wikipedia is much more than any of us have read, right? So GPT-4 has roughly looked at all the text available in English, okay? So if you think about this scaling factor, it's very strange that they are so far away from understanding the world in a way that matches you and me, okay? The cost of it is the other factor. So we are caught now in an arms race between US and China with building bigger models. GPT-4 costs about 100 million to train, okay? So this is huge. So if you wanted to build your own GPT-4 using medical data or biological data, you have to spend an enormous sum of money if you're starting from scratch, okay? So it's not a race you can win easily. So the good thing is maybe this is reaching a plateau, okay? So for instance, a whole bunch of different articles have come out that have criticized GPT-5, okay? So for instance, some people are saying GPT-5 is just not as good. It's very overhyped, right? But it's not delivering on the promise. You have to keep in mind that the goal that these companies say is to build artificial general intelligence, okay? Which is the idea that the AI has as much common sense and understanding as we do. And it's very far from that, okay? So, you know, people make promises, right? So, you know, the CEO of OpenAI said, we'll build the next GPT, which will be really good, but there's no clear vision on how that's going to be achieved, and the only idea they have is to throw more data at it. There were two other interesting papers I've linked in the bottom. These were by companies. One was by Apple, and the other is by Salesforce. And they came up with an analysis across these models, and they showed that they're very poor in understanding simple problem solving. Okay? So again, if you think about the fact that it has as much connections as the human brain, but doesn't even answer questions like a 5-year-old on some things, it's a shocking difference, right? The other interesting thing is the amount of energy the human brain uses is the amount to power a laptop, okay? But the amount of energy you need to use to train and run one of these large language models is immense, okay? So there's a huge difference in cost scale compared to our human brains, which is very efficient, okay? The other interesting thing, I think, is also from the perspective of the way we use ChatGPT. So people are starting to talk to ChatGPT like they would talk to humans, okay? Now, this is very problematic because the output patterns of ChatGPT is not a commitment. So again, as I said, if I ask you who did you vote for as a political party, you'll have a reason to choose. You have a defense, right? So I could attack you based on your identity if you choose for a political party. But with ChatGPT, there's no such commitment. You change the prompt, it could come up with an entirely different answer, right? So you could say, who should I vote for if I believe in climate change? And it might say party 1. But I say, if I add, who should I vote for if I believe in climate change and I'm wearing a red shirt? It might say party 2, right? Which is a very strange hallucination to make and has no connection to the question you've asked, okay? So this is the reason that I feel people are, and on the more scary side, there have been cases of people committing suicide because they got the wrong advice from ChatGPT, okay? Again, the designers don't want this to happen, but the way these models hallucinate leads people to think that they are real individuals behind there, and they make the mistake of making a commitment, and that's when you pay the price, okay? So all of these are limitations, and I don't think it's easy to get around these limitations, okay? So neuro-symbolic AI, in a way, is a kind of response. It's not saying let's replace it. It's saying let's augment it. And the reason we need to augment it is that humans are algebraic systems, okay? So for instance, if I tell you what's going to happen if I throw this water bottle, you have a geometry model in your head. Even if you know nothing about geometry, right, that it's going to come towards you and fall towards the ground. So you don't need to remember the laws of gravity. You don't need to remember the laws of geometry, but you have an intuitive understanding of how the world works. So we call this symbols, okay? We think in terms of symbols, not that there's a symbol in our head, but the way we move things around is a bit symbolic, okay? So neurosymbolic is basically saying, let's take the neural stuff, but let's add a symbolic component to it, so we can understand the structures of machine learning models, okay? So there's a wide variety of things here. There's no single thing. So in a way, you can see this as challenging the scaling hypothesis, right? The scaling hypothesis is throw more data centers, build bigger things, it's going to work. Whereas the hybrid approach is to say, hey, hold on, let's try and think if you can build around the neural network to make it work, okay? The other interesting thing is there's a very famous cognitive scientist called Daniel Kahneman who won the Nobel Prize, and he had this idea that the way the human brain works is in terms of system 1 and system 2, okay? So system 1 is very quick. So if I touch a hot surface, I move it away. So it's very reactive. Or for instance, if I see a car coming in front of me, I know instinctively that it's going to hit me. What I do next it depends on my training, right? Or my ability to respond. Whereas system 2 is kind of slower, okay? So if I ask you, what's the best way to get from here to Barcelona, you might think, is it better to drive or is it better to take the train? So there's system 1 and system 2, and you can, in a way, you can think of this also as the connection between machine learning and symbolic. Machine learning is fast because it's trained on data, and symbolic could manipulate things and build around it, okay? Everybody with me so far? So here's a much more complicated picture. I apologize for the complicatedness, but I just thought I'd give you the whole picture, what it looks like. As I said, what you saw initially was the left-hand side. where we had inspiration from the Greek philosophers. We had deduction, induction, and abduction. Now we have all of this work on machine learning, and there is actually quite a nice overlap, because if you think about it, humans learn, right? So for instance, I might tell you my phone number, and you've registered it. But on the other hand, if you keep seeing me go for some water, you might learn that I'm thirsty. Okay, so humans learn as well. Now, you can come up with a kind of algorithm or paradigm that can connect machine learning and logic, and that's completely fine. But neuro-symbolic is specifically saying, let's look at the deep learning side of things, including large language models, and see what we can build around it. Okay. So that's the small brown circle right at the corner, okay? There are some more technical connections there. I won't go into it, but if you're interested, please send me an email and I can give you some details, okay? Here are some examples of what you can do with neuro-symbolic, okay? So the left-hand side, maybe some of you may have seen this, but this is protein interaction. So if you look inside our body, we have molecules and proteins that interact with each other. And depending on what we're experiencing or what kind of genes we have, there's some kind of interaction. So biologists have been studying this for many years, and they build these complicated networks. They call them ontologies. Okay. Now this is a great piece of knowledge that I don't want to throw away. So if I'm building a machine learning model, I want to be using this as much as possible. And neuro-symbolic would say, let's come up with a way to integrate an ontology in the machine learning prediction. Okay. The right-hand side is an extremely simple example, but it turns out to be quite hard for deep learning networks. Okay. The right-hand example is this case where you want to avoid something, and some places are safe, some places are dangerous. So you could think of a robot that's moving around. It wants to avoid touching humans, right? But it can walk around in this space freely. Okay. So how do you get a system to accept these constraints? Okay. The third example is things like discovery. Okay, scientific discovery is about understanding the laws of nature. And usually before machine learning, people would sit down with a piece of paper, they would look at observations and try to come up with equations. What if you could learn these equations by themselves? Okay, sorry. Did somebody say something? Oh, okay, that's fine. So it's about discovering these equations from data, okay? Let's look at this thing on the right-hand side. It should give you an idea. It's a very simple example, but it should tell you how complicated it becomes, okay? So this is a case where I have a little rectangle, okay? I have these blue regions here, and I want to make sure all my predictions fall into this blue region, okay? If I ask somebody from high school geometry to describe this, it's quite easy to write it down. You look at the x-axis and the y-axis, you write down some numbers, you draw the rectangles, right? But it turns out to be incredibly hard to get a machine learning system to do this, okay? So why is that? The reason is that the way these machine learning systems work is that you feed them data, and you tell in this data what is positive and what is negative, okay? So even if you told the model that those are the positive things, the trouble is that the number of negative things are so large, right? It either completely overshadows the positive examples, or you simply cannot provide so much data, okay? So we need a better way to integrate this idea into the network. So the idea here, again, I apologize for the equations, but it was just to give a little bit of clarity and concreteness. The idea here is very simple, okay? So usually when you train this network, you penalize the network every time it misses the pluses and the minuses. What I'm now going to say is, along with making sure you agree with the pluses and disagree with the minuses, also respect the geometry, okay? So it's got two functions now. It's trying to optimize for the plus and the minus, but it's also trying to make sure it fits into this geometry. And what turns out is that you have a dramatic improvement, okay? So the bottom one is if you train the model without any constraints. And as you can see, you get lots of invalid examples because it's so large, okay? But once you throw the constraint in, you start fitting only the proper ones, okay? You might think this is an abstract example. What is it used for? So one case it's useful for is to think about fairness. So around 2010, people started discovering all data we have is basically biased. Okay, so there are lots of historical biases, usually against gender, but depending on which demography you go to, sometimes it's against minorities and so on and so forth. So one definition of fairness, in the sense of balancing things, is to say that if you have two job applicants and they have the exact same profile, so they graduated from the same university, have the same scores in all the subjects, you don't differentiate between men and women. Okay, it's a very simple idea. Now the question is, how do you get a machine learning model to respect that? Okay, so the neuro-symbolic approach here is to basically look at the data and you write down this constraint as a symbolic constraint. Okay, so it's a bit hard to read. I think it's for some reason the screen's blurring it a little bit, but I'll try reading the one on top. So what it says on the top is, for every point, if I look at another point that's exactly like that, except that the gender is different, I don't change the decision. Okay, so it's just making sure that two identical people, their gender removed, would not be treated differently. And you train the model, and of course then it not only do you get high accuracy, but you also get gender parity. Okay, so this is a reason why the symbolic thing makes sense, because you train the model, but the symbolic aspect is adding some common sense knowledge into the thing. Okay. I won't go much into the opposite side of things. So this was enforcing the constraint, but as I said, you want to discover things from nature. Okay. So we've done some work where, for instance, you might discover something like the theory of relativity equation from data, things like E is equal to mc squared. Okay, so you look at data, you find the way mass, speed of light, and energy and other factors relate to each other, and you extract the equation from it. Okay. Another place you could apply this is if you were training a robot, for instance, and you were showing the robot what to do, and you wanted the robot to learn a policy that captures your intuition. Okay. So it would look something like this. It would say, when I'm in a certain position and I'm looking this way or that way, I turn a left, otherwise I turn a right, right? And the advantage here is that you can extract this policy, you can read it, and you can say, is this what I had in mind when I was training the robot? Okay, so there's a huge advantage of having that explainability factor when you build these models. Okay, so what's going to happen next? Hard to say, all right? So in a way, the neuro-symbolic paradigm is touching the surface, because it's basically saying, let's look at machine learning models and let's try and deal with the variables in a symbolic way. But if you think about how humans work, a lot of our interaction is based on beliefs. Okay, so I choose to say something because I have certain beliefs about where I am, who I'm talking to, and so on. If you ask me for an explanation, I'm not going to, give you a random explanation. I'm going to think about what you're asking me and respond to that. So in a way, if you think about the future of, building systems, it has to talk about beliefs, right? It has to talk about an idea of what information the system has, what information all of you have, and how they interact. Okay, we live in a dynamic world, right? So there's time and space and actions, and all of these need to be factors. They all need to be citizens in the model. Okay, as I said, causality will play a big role, because the way much of the world works is in terms of a causal connection, and we have not yet extracted or tapped into it richly enough. Okay, so that could be a huge role in making sure machine learning models work. One interesting thing is, of course, in a way, if you look at old computer science textbooks, they often talk about the balance between expressiveness and computation. So the richer the model is, harder it is to compute. You cut down things, it becomes easier to compute. So what's the right balance there? Okay. I thought I would end with a few slides on turning back to large language models. So as I argued, by themselves they're very problematic. But what if they could be used as a kind of mechanism to get intermediate results? Okay. So I'll talk about the idea that large language models could be used for generation. Okay. So the way we started on this, again, the font is a bit hard to read. But what this little example is, it's about a card game. Okay, so we have a set of cards on the table. We're all playing poker. Okay, I lift a card. Maybe I show it to my colleague. Now you're looking at the card and you're thinking, does that mean they'll start sharing secrets and try to, outbid me? So there's all of this mental stuff going on, right? Now, can you get an LLM to do this? And the answer is usually no. Okay, depending on how complicated the scenario is, you'll get some very silly answers. Okay, but one thing you could do is you could use a large language model as a translator. Okay, the translator takes things in natural language and produces some sort of mathematical language that's easier to understand and you can do computations on. Okay, so in this case, again, very small, I apologize for that, but it translates to something called as public announcement logic. Okay, so it's a logic, it's a mathematical language for talking about agents and their beliefs. Okay, it's not an abstract thing in the sense that it is a well-defined language where you can talk about what each person knows. Okay, now it turns out you can exploit this in the following way. Okay, so classically you have a theory of mind problem, that's what it's called when you're thinking about beliefs, and you give it to the large language model. You could try to solve it by the large language model itself. Most likely it's going to fail, but then you do the translator, right? You use it as a translator, you get the translation, you solve the translated model using a mathematical solver, and you compute answers. Okay, turns out this has dramatically improved the accuracy. So if you use the large language model as it is, you roughly get a little better than random. Okay, so 58%. You use a translated system, you suddenly shoot up to 91%. You might be wondering, why is it not 100%? And the reason is because the large language model might make mistakes in the translation. So once you fix the translation aspect, you could then completely rely on the mathematical solving to get exact answers, right? Does that make sense? So interestingly, there is a classical problem in computer science, which is the problem of the difference between so-called easy problems and hard problems. Okay, so easy problems are something that can be solved obviously in easy time. Okay, one way of thinking about it is if I'm trying to, if I show you a Sudoku solution, right? You look at it and I say, is this a good solution? It's easy for you to check because all you have to make sure is that no numbers are overlapping or the two numbers don't appear in the same row or same column. But generating a correct solution is hard. Okay, so this becomes a class of problems called as NP-complete problems. So see, these are the hardest problems in computer science. Okay, so cryptography, right? It's an NP-complete problem. So in a way, when you use something like 128-bit encryption, we can trust that it's secure because to break it is going to take as much time as the universe has been, running for. Okay, unless we come up with a magical algorithm that can beat that assumption. Okay, so I'm not saying AI is going to come close to that, but the interesting thing is, what if you use large language models as a way to generate solutions, because it can generate things rapidly, but the checking is done using symbolically. Okay, so you get into this interesting space where you have a meta framework where the large language model generates things, but you use symbolic solvers to fix them. Okay, so this is another way where you can think of a hybrid solution between deep learning and symbolic systems. Okay, I wanted to also briefly talk about different perspectives on neuro-symbolic AI, but not just neuro-symbolic AI. Okay, so one interesting development was there's a mathematical solver called Wolfram Alpha. Now this was very powerful, through to the 2010, 2020, ChatGPT came and it tried to do some of these problems on their own. So one thing they were looking at is integrating ChatGPT and Wolfram Alpha. So you write things in natural language. Again, it translates it into Wolfram Alpha and solves it. So what's an example? So you might say, what's the projected economy for Valencia in 20 years? Okay, Again, Wolfram Alpha might be able to do some of these projections, but it can't understand the natural language. So you use ChatGPT to translate it and solve it using, Wolfram Alpha. Okay, so that's an example of neurosymbolic. Alpha Geometry is a solver from Google DeepMind, which solves Olympiad-level geometry problems. Again, this is a neurosymbolic approach because they look at the question, they translate the question into something that a geometry solver can understand and solve it exactly, okay? There are various, if you've ever gone into coding, now there are various examples of using code interpreters. These help you write code, okay? Again, you write your specification using ChatGPT, but then it goes to the code interpreter and gives you the right answer, okay? There's some claim that by Arthur that maybe neurosymbolic AI could be the approach for solving the hallucination problem with large language models, okay? Now I want to say that this is not the only view of fixing deep learning systems, okay? So if you look at some other proposals, people talk about all sorts of facilities that human brain has that we haven't yet engineered, okay? An example is memory, right? So we have static and dynamic memory. Sometimes we have long-term and short-term memory. We also have abstraction, right? So for instance, if I ask you about, how politics works, again, in Spain, you're not going to start by explaining to me how agriculture works because there are two different levels. There's macro and microeconomic explanations for certain things. So humans understand that there's abstraction, but we haven't found a good model for abstraction with machine learning. Likewise, we have hierarchies, right? So for instance, we understand that some things are more important than others, some things are more expensive than others, and we can do comparisons. So again, we don't have a good way to understand how to work with those categories, okay? So the takeaway is that, neurosymbolic AI may be one approach to having this thinking fast and slow. But again, we are so early in building this. There is so much we don't understand about human cognition and how to map that back into AI. So this is just the very first stage, okay? As I said, we have issues of explanations and correctness. Maybe neurosymbolic AI could be the answer here. We need a lot of new work. There's, AI is not going to be solved in the next couple of years, I think. So we have a lot of new work to be done, a lot of new ideas that might come from psychology, might come from cognitive science that we haven't even touched. So it's an interesting and very exciting space to be. And finally, if large language models are still around in 5 years, which I think they will be, then we will need to think about better ways to work with hallucination and other problems, okay? Yeah, that was me. Thank you very much for listening.
Again, I think that microphone loves me. Any questions here? There you go.
Very nice talk. Thank you.
Thank you.
Just on this slide, can you expand a bit on some of these ideas when you say new definitions and semantics, for example, or this idea that cognitive science might contribute? What, as a yeah, perdón. Thank you. Hola. I was suggesting you expand from the point of view of a computational scientist. What do you expect to come from cognitive science, for example? As what do you want to get?
Yeah.
And then expand on this point of the semantics needed.
Yeah. So from cognitive science, one thing we know is that, based on the experiments that done for the last 30 years, as I said, we have some very interesting experimental data on how people understand abstractions, how people are fooled by certain things, right? So there are cognitive deficiencies and illusions that we deal with. We don't yet know what is the way to understand those mechanisms in a mathematically precise way as relevant for AI, right? So as I said, we don't have a good architecture yet, but thinking in terms of memory, thinking in terms of short-term versus long-term memory, thinking in terms of how we recall right? So if you tell me something, and in 5 years later, if you say, do you remember we met in Valencia? And I will remember some things. Maybe I will even remember the color of your jacket, but maybe I would have forgotten what you asked me or what we spoke about, right? So how does that work, right? I'm not saying we need to translate that into AI, but I think we need to understand that humans are so good at common sense and so efficient. I mean, if you think about how children learn, right? In the beginning, they just babble, maybe until 2 or 3, and then they pick things up very quickly. I mean, you don't explain the laws of gravity to a child, but at some point they understand that they throw things fall down. But no machine learning system, I mean, unless you try to engineering it, works out that just because it's seen pixels of things falling down, gravity is at work, right? For it, gravity is just an abstract label that you are telling the data. It has no meaning, it has no way to understand the meaning of that. So that's what I mean, that in CogSci, how evolution has given us these incredible powers, and what might we learn from that, and translate it to AI is an interesting question. I don't think it's biology itself, right? So for instance, when we think about planes flying, we haven't engineered planes to work like birds, right? Although we know how birds fly, right? I mean, we understand we can build a mechanical bird and make it flap its wing, but that's not how an airplane works. So we need to understand the laws of aerodynamics. And the same way we might have to understand the laws of memory, evolution, learning, and use that as inspiration to code that into AI, right? I mean, again, there was a time when this was happening. In the 80s, there was a very healthy discussion between psychologists and cognitive scientists and AI. It kind of died down for a little bit. Maybe it gets picked up again, right? In a way, large language models said, we don't need you guys, right? We'll just throw the data and we'll get the answers we're looking for. And now it looks like that's not the case. So, we might go back. Regarding the semantics, it's a very simple thing, right? So as I said, neural networks look like human neurons, but they are not the same, right? Human neurons are bidirectional. Neurons work in a single direction. Now, what would it mean for us to think about different architectures, and how do we make that translation from that architecture to symbols, right? Computation is discrete. So it works with symbols. On a computer, you write a piece of code, it executes it, so it's all discrete. How do we go from this network, which is inspired by biology, and make the connection to symbols, right? I am doing it in the work by looking at it from the top and saying, maybe that's a symbol and maybe that's a symbol. But if it has to organically emerge, that's nobody's figured that out. In fact, we don't even know how it works in our brain. Right? So we don't know how we do the things we do. I mean, you can see the brain firing when I, pick something up, or I get very excited, or I get very sad. But they don't know what that means. How do you translate that into concrete objects that you work with, right? How do I can think about my emotions as an object, right? I can say, I was sad today, I was happy today, and if I do this, I will get happier or sadder, or whatever it is. How do I do that, right? So there's a very difficult question that we haven't figured out with human brains, and maybe it's an inspiration.
I enjoy your talk, and I fully agree with a need to maybe symbolic systems to go beyond. In one of your last slides, you quote somebody more or less saying that the solution or the third wave of AI would be somehow combining good old-fashioned AI with LLMs, and that one, yeah. And as you know, the topic of our panel discussion afterwards would be embodied AI. But you know that at the last decade of the last century, the so-called new AI, embodied AI, was opposed to good old-fashioned AI. So I would like to hear your thoughts about how to add embodied AI to this combination of generative AI and good old-fashioned AI. Thank
Yeah.
you.
Yeah, thanks very much. I mean, I don't want to suggest that neuro-symbolic AI is the answer to everything, right? That was not quite my point, to just say that, you know, even neuro-symbolic AI in a way embodies the limitations of deep learning because you're building around it, right? But putting that aside, coming to your question, one of the things that, you know, neuro-symbolic AI is very concerned with is building a world model. As I said, a large language model doesn't quite have it. A world has objects and properties, and we have a way to write some of these down mathematically, but an embodied agent might discover them either through a simulation or through interaction. And it might not know the name of things it touches, or it might not even know the names of things it sees. But there is obviously a link we need to make between that perception, between that touching, to how that relates to my world of objects and properties. So I think there's a symbol grounding question that deeply is tied to this whole neurosymbolic approach. And there are people who look at this. I don't think there's a good answer. And again, this is a surprising thing, because once you accept that human brains don't actually have symbols, it becomes a very nebulous question. What is the role of symbols, right? So there was one book that came out in the 1990s called The Algebraic Mind. And the idea was that, you know, humans largely have an algebraic way of thinking. In fact, Gottfried Leibniz, back in 1600s, he was thinking about thought as a computation, as a symbol manipulation thing, right? So we don't know how that happens, right? I mean, even though the world is continuous, we seem to somehow take that and make discrete objects in our heads. When I look at you, I'm looking at one individual. I'm not seeing you as the waves that are coming out of your body, right? And that's a very interesting thing that evolution has given us, right? Because everything is continuous, right? In principle, I should just be seeing light everywhere, and a voice coming, and even a voice is a spectrum. But for me, you have a voice that's distinct from your neighbor's voice, and you have a body. So there is a connection from that perception data to something that becomes discrete. And the connection to symbol grounding in neurosymbolic AI may be how we approach that question.
Well, I think that we're running out of time. I don't know if there's any other questions. That's it? Well,
I think
here. That's the last one. Can you just stand up?
Yes, okay. So a very quick one, thanks for the talk. It is about scalability. I mean, you mentioned the problems of scalability of systems, but from an industrial perspective, the neurosymbolic is a very appealing and very interesting approach, but can we really scale up to industrial level? Because we know that symbolic systems have tremendous limitations in the level of complexity. Can we convince industrial people that this is the way to go?
The short answer is yes, in the sense that industry people are already using things like SAT solvers, optimization, constraint solvers, and so on. I think the question is of granularity, right? So we are not going to be able to symbolically manage a high-dimensional image. But if you abstract that into a single atom in the symbolic language, then symbolic solvers can go to millions and millions of propositions, no problem, right? So we need to figure out that, you know, the balance between taking very large, continuous, high-dimensional data and massaging it to something that is expressible with using a few symbols, even 1,000 or 1,000,000 variables, and it might just work, right? So it's just a question of balancing that act.
okay.
Thanks very much.